Today on How It's Made. Noise barrier walls. Front load washers. Bourbon. And flexible circuit boards. To contain the sounds of traffic, it's often necessary to put up a wall of silence. Noise barrier walls both absorb traffic noise and shield neighborhoods from it. With stone or brick-like textures on both sides, they even look good on the street. In the 1970s, noise barrier walls were mainly drab concrete. Fast forward to today, and the walls come in a range of textures and designs for curb appeal. But of course, it's their noise-absorbing qualities that really improve the neighborhood. They're made from a wood shaving and cement material that's very porous, which allows the walls to absorb sound and entrap it. Production starts with the raw shavings. A conveyor delivers them to a hammer mill. Inside, rotating hammers force the wood shavings through a cutting screen. This carves them into smaller particles of various sizes. It's this combination of sizes that will create the noise-absorbing pores in the completed wall. They test a proprietary chemical solution that will be used to treat the wood particles and confirm it's the right concentration. An auger then mixes it into the wood particles until they're damp and thoroughly coated. Without this treatment, the wood particles wouldn't bind with cement. It will also protect the wood from decay. In another mixer, they add water and a second chemical solution to further enhance the binding process. The wood particles are now primed and ready to be mixed with a powdered mix of limestone clay called Portland cement. The machine works the ingredients until they form a cohesive material that can be shaped. The next worker sprays a release agent onto the stone pattern liner. Each mold will form one noise barrier panel. The team transfers the wood and cement blend into the mold. They work at a steady pace to fill it before the mixture begins to dry. Once they've filled it part way, they level the wood cement material, then compact it with a tamping tool. Next, they add a steel mesh. This mesh will serve as a skeleton, allowing the wall to stand strong. They pour freshly mixed concrete onto the steel mesh. It flows through the mesh and onto the sound-absorbent mixture below, binding the two layers together. The worker spreads the concrete throughout the mold. He pierces the surface with a vibrating tool. The vibrations consolidate the concrete and eliminate air pockets. The two-person team levels the concrete layer using a wood screed. They apply a second layer of the noise-absorbing material and level it. They lower the stone pattern press lid, which will mold the pattern onto the top side of the panel. They set a 10-ton concrete block on the mold, and pressure forces the mold patterns onto both sides of the casting. After a few minutes, they remove the lid and the imprint is revealed. They quickly cover the panel surface with a plastic sheet to prevent any evaporation of moisture as the cure continues. If the blend cures too quickly, it could crack. After another day, they remove the tarp and they're ready to extract the panel from the mold. A crane lifts the panel and sets it aside to cure for about a month. Built panel by panel, these noise barrier walls can become a substantial fortress, providing a solid defense against noise pollution. Front-loading washing machines use far less water than standard washers. They're gentler on clothes because there's no agitator in the middle of the drum. The spin speed is usually about 20% faster than the standard top-load machine, so the clothes come out of the wash drier. With gravity helping tumble the laundry, a front-load washer is gentler on the clothes while using less water. Its design can also accommodate a larger capacity drum, so you can do bigger loads. The washer's cabinet is made of steel. A washing machine is routinely exposed to moisture, so they use galvanized steel which doesn't rust. The cabinet base is comprised of 4 pieces, which together provide more structural strength than a single piece would. At the corners, workers install 4 screw-in rubber feet which are height adjustable. This allows the washer to level on an uneven floor. Next are the 2 side panels. They are already stamped to the required shape in a press and coated with baked-on paint. This automated machine installs brackets on the inner side for mounting components later on. The next automated machine attaches the side panels to the cabinet. Rather than welding the edges, which would ruin the paint finish, the machine's punch tools mechanically lock them to the base. A robot then transfers the cabinet to the assembly line. Here, workers connect the side panels with a structural support bracket and power cord already installed on it. Workers prepare the rear portion of the machine's 2-piece plastic tub. First, a robot mounts a steel bearing on a press. The press then forces the bearing into the hole at the bottom of the inside of the tub. Then the process is repeated, but on the outside of the tub. This pair of bearings seals the hole to prevent leaks and enables the stainless steel wash drum to spin. To counterbalance the spinning load, they weight the front of the drum with a plastic ring containing heavy steel balls suspended in fluid. Then they insert the shaft at the base of the drum into the tub's bearings and cover the top of the drum with the front section of the tub. It has a rubber gasket called a bellow. The bellow forms a leak-proof seal around the drum. After welding the tub sections together, they mount the washer's motor to the rear. In this stator rotor motor, the electric current travels through the coiled copper wires of the motor stator, generating pulses of electricity. Those pulses push on magnets lining the motor's rotor positioned on top. The magnets repel the pulses, and this repeated pulse repelling drives the drum in the direction and speed required. Next, they install a drain hose on the side of the tub and attach it with a retainer clip. They bolt a piece of concrete to either side of the drum opening to counterbalance the weight of the motor on the back. Then they turn the now complete wash unit on its side and install it in the cabinet. Next, they mount the drain pump in the cabinet base and connect its wiring. The pump's job is to remove dirty water from the tub. 4 shock absorbers are installed between the bottom of the wash unit and the base. These large pistons dampen much of the vibration during the wash and spin cycles. Next, the front panel. Like the sides, it's made of a stamped sheet of galvanized steel with a baked-on paint finish. They install and connect the console, which houses the machine's central control module. They pull the bellow on the drum all around the front opening to seal the perimeter. They secure it in place with a wire retainer clip. The hinge door has a see-through plastic window. Like the rest of the machine's metal parts, the door panel and hardware attaching it are also made of galvanized steel. The back panel is left unpainted. After feeding the power cord through its hole, workers screw the panel to the rest of the cabinet. Then they complete the cabinet with the top panel, which has the baked-on paint finish. The front-load washing machine is now all set and ready for its first load. Bourbon whiskey is uniquely American. The U.S. Congress officially recognized it as a product distinct to the nation. This amber-hued brew was first cooked up by Scottish and Irish settlers in late 18th century Kentucky. Today, production continues there with the approval of Congress. The American government regulates the making of bourbon to keep this native spirit true to tradition. By law, it must be made from a grain mix that's at least 51% corn. Distillers often use more for flavor. Shakers sift out cobs or other foreign material, and the kernels head into a grinder. Inside, rollers crush the kernels to release the flavor of the starch. The process leaves larger chunks of the corn germ and husks. Once distilled, these bits will settle out. In separate batches, the machine also grinds malted barley and soft red winter wheat. They cook the corn and blend it with limestone-rich, iron-free Kentucky water. They add the barley, winter wheat, and a bit of mash from a previous batch. Along with a special yeast formulation, the grain mash flows into fermentation tanks made of cypress wood. After 8 to 10 hours, the yeast works its magic, and the mash becomes a bubbling brew. The bubbling is caused by the release of carbon dioxide gas as the grain sugars ferment and become alcohol. After 3 days, it has fermented into a thick liquid they call distiller's beer. They pump it into a column still, which boils off the alcohol, leaving water and other substances behind. The alcoholic vapor rises up to be condensed into liquid. After distilling it a second time, the alcohol concentration rises to a strong 130 proof. It's clear with no noticeable color. At this stage, they call it white dog. Once water has been added to dilute the whiskey to 110 proof, an employee takes a sample and sends it to the lab. There, a technician places a test tube of the alcohol into a gas chromatograph tester. It vaporizes the alcohol and then analyzes the flavor compounds and alcohol strength. With approval from the lab, they're ready to barrel the batch. They pump it out of storage tanks and into new oak barrels that have been purposely charred on the inside. Charring caramelizes naturally occurring wood sugars to add sweetness to the alcohol as it ages. It will also turn the clear alcohol an amber color. Once corked with a walnut stopper, the employee rolls the barrel into a multi-tiered warehouse. Here, the bourbon will age for many years. Partway through, they'll move the barrel to another level of the building due to temperature variations. This will make the product more consistent. After 6 to 7 years, they uncork the stopper and insert steel tubes to draw in ambient air. This causes the bourbon to flow freely when tipped, and it gushes into a trough. The alcohol has ripened to a sweet caramel-colored brew. After they add more water to make it 90 proof, it's ready for bottling. Nozzles fill the bottles with bourbon right to the neck. The bottles then circle over to the cap applicators. The applicators spin metal caps, screwing them onto the bottles. The bottles then ride a carousel, and a device picks up and applies the labels. A brush smooths them to the bottles. Down the line, a two-person team retrieves the bottles and dips the caps in hot wax. The wax quickly dries and solidifies to give the bourbon a better seal. After several years in the distillery, this Kentucky bourbon has come of age, and that calls for a toast. The circuit board is where the electronic components are located, along with the electrical connections which power them. In a larger device, such as a computer, the circuit board is typically rigid. When the device is compact, like a small camera, the circuit board must be flexible. It needs to fold to fit inside. Flexible circuit boards are so thin and pliable, they're nicknamed origami circuitry, after the Japanese art of paper folding. At the core of the boards is a hair-thin polymer film that's both bendable and heat-resistant. The manufacturer produces this material for several industries. In this case, they cut rolls of it to the width required for making flexible circuit boards. With a rigid sheet of paper lending support from underneath, the film enters a machine which sandwiches it between two thin sheets of copper. A cutter then slices the sandwich into rectangular sheets. A cushion of air pumped through the conveyor belt literally floats sheet after sheet off the machine and into a stack. Each three-layer sheet is separated from the next by the support paper called a laminate. The film at the center has a heat-activated adhesive coating, while the adjoining copper surfaces have been chemically roughened to enhance adhesion. After drawing the layers tightly together with a vacuum, workers place the laminates in a high-temperature, high-pressure chamber for several hours. This activates the adhesive, bonding the layers. To test the bond strength, they burn some adhesive off a sample of finished laminate to pry apart the layered edge. Then they grab the top copper layer with this pulling device and measure the strength required to peel it off the film. The laminates now ship to a circuit board factory. Here, computer-guided machines cut them into specific sized panels and drill tiny holes for mounting the electronic components. Then a coating machine uses a combination of heat and pressure to apply a light-sensitive fluid to the panel surface. Technicians load the panel into an exposure machine, in which a computer-guided laser scans the circuitry pattern onto the coated surface. A laser is a beam of focused light, so wherever it hits, the fluid reacts and hardens. The dark areas of unexposed fluid remain soft. The next machine acid washes the soft areas, removing both the fluid and the copper layer underneath it. Now the only copper remaining on top of the polymer film is in the circuitry pattern. This inspection device meticulously checks every single copper circuit. Next, they remove surface dust with a sticky roller. The panel must be pristine before receiving the sheet of electrical insulation, a mere 25/100ths of a millimeter thick. Technicians use a magnifier to carefully match up alignment holes on the film with corresponding alignment holes on the panel. By activating the film's built-in adhesive with a soldering iron, they tack the insulation to the panel at key spots. The next step is to fully laminate the insulation to the panel. Technicians sandwich two panels at a time between sheets of protective plastic. This protects the surfaces from the heat and weight of the lamination press. As it forces the insulation film deep down onto the panel, it encapsulates the circuitry. They load the panels into the lamination press, apply a vacuum to remove the air between the layers, and start her up. For the next hour and a half, the press simultaneously applies high pressure while heating the panels to 400 degrees Fahrenheit. When the panels cool and come out of the press, technicians place one at a time on a circuit board-shaped die. Then they release a press, which forces the panel onto the sharp die, slicing away the excess material. The flexible circuit board is now ready for the company that installs the electronic components. There are two ways to mount components. Solder them directly onto the board surface, or solder tiny prongs underneath the components known as leads into the board's mounting holes. A flexible circuit board can have as few as a dozen components, or as many as 500. Technicians can solder larger ones magnified under a microscope. But only robots can solder smaller ones because they're so tiny and barely visible to the human eye. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.